So this will be the video for the solution to question 8 on the 116 exam 1 winter 21, and this question is moving into sort of the end of chapter 14.6, which talks about damped oscillations. So we're looking at sort of the exponential sort of decrease in the amplitude of an oscillator when it's subject to sort of resistive forces. So the amplitude at some given time t is given as the initial amplitude e to negative t over tau, where tau is the damping constant, and that's what sort of the key ideas that are expressed or sort of trying to sort of address in this particular exam question. Okay, so let's look at the question itself. So we've got a group of 116 students are taking position measurements for an object moving along the x-axis while it oscillates under damped conditions. So that's sort of one of the that's key sort of idea that this is a damped oscillator. After collecting the data, they form the position versus time graph below, but due to a glitch in their software, the data between 2.5 seconds and 5 seconds was removed. So we can see here we're missing some data. Using the information in the graph, where is the object located at t equals 4 seconds? Assume the period of the oscillation is not affected by the damping. So we can see that the period is 2 seconds. So let's open peak to peak here. So this is uppercase T. So I expect to be some other peak at t equals 4 seconds, 2 seconds later, and expect it to be lower than 2 centimeters on the x-axis and greater than 0.5. So if I want to find exactly where the position is, I can go ahead and solve for that. So if we're thinking about our expression as we said from the previous page, a of t equals a0 e to the minus t over tau. So we do have a0, it's 4 centimeters. And I think that was true for both versions. Now, the same method of course will apply here. So we can use the information either at 2 seconds or at 6 seconds to solve for tau. So if we take a of t divided by a0 is equal to e to negative t over tau, and then take the ln of both sides, the ln of a t divided by a0 will equal negative t over tau, and then tau will equal negative t divided by the ln of a t divided by a0. So that will of course apply to both versions of the question. If you got a version it was slightly different than this version. So in this particular example, I would probably pick the 2 seconds here, and note that the a at 2 seconds happens to be equal to 2 centimeters. So looking at a over t will be half, so taking negative 2 seconds for the time divided by the ln of 0.5 is give us 2.89. And then we can solve for the a at 4 seconds to be equal to 4 centimeters. That's the a0, e to the minus 4 seconds over 2.89 seconds, the tau that I would have here, and it turns out to be exactly 1 centimeter. So the object is located at x equals 1 centimeter. And I think in the second version it's also at the equals, I think it was 0.5. I just can't exactly remember the values, but it's of course the exact same method. I just changed the numbers slightly in the other version. But you can go through the same process. You can use one of the peaks to find the value of tau, knowing that you have this sort of amplitude at that particular value. Assuming that again we're told that the period is not affected by the damping. That's not necessarily true, but we'll just make that assumption for this question. Going through the same type of math and then solve for the basic x position at a given time. And I'm giving it was at both versions. The time is at a particular a multiple of the period. All right, yeah, I'll wrap the question up there and follow up with question 9.